ELEC2 2019 question 3. The following diagram shows the structure of an audio system. Well, audio systems are very popular questions. You'll probably find if you look back over the last 6-7 years worth of papers, they occur in every single one of component 2. The preamplifier for input 1 consists of 2 non-inverting amplifiers as shown in the diagram. Now, for part A, that diagram is a classic diagram, normally shown where one amplifier is insufficient for the gain needs, but what we need to realize is that the bandwidth of the individual amplifiers is maintained through the system. The circuit diagram for each is given below. Well, we've got a picture of that particular circuit diagram, and what we need to realize when looking at this is that this is a non-inverting amplifier. And so for part 1, the question asks, the op-amps have a gain bandwidth product of 3 MHz. What is the overall voltage gain and bandwidth of the preamplifier? Well, for voltage gain, what we need to realize is that we're going to use the equation that gain is equal to 1 plus RF over R1, where RF is 750 kilo ohms in this example, and R1 is 30 kilo ohms. So we can find out the gain of this. So it's 1 plus 750 over 30, and that gives us a gain of 26. Now that is the gain of the individual circuit shown above. So the total gain of our system is going to be 26 times 26, because the first amplifier amplifies 26 times, then amplifier B amplifies that output 26 times. And so what we end up is with a total gain of 576. Now for the bandwidth, we don't need to think about the 2 individual op-amps. We can just deal with one, and the gain bandwidth product equation enables us to find that bandwidth is equal to gain bandwidth product divided by gain. And so we've got 3 MHz, or 3 times 10 to the 6, divided by 26. So rather than the 576 for the 2 amplifiers, we're just going to use the gain of an individual amplifier, and this gives us an answer of 115.4 times 10 to the 3 hertz, or 115.4 kilohertz. Okay, so part 2, the preamplifier includes 3 capacitors. What is the function? What is their function in this circuit? Well, capacitors in this particular configuration, what they're meant to do is to block DC signals from transferring to the next stage. What you can think them as is they're passive high-pass filters, and so they block low frequencies. And if you think between those capacitors and the 0-volt rail is an infinitely high resistance, then the actual their ability is very, very good at blocking very, very low frequencies. Okay, B part 1. A first-order active filter is used in the control block to boost those parts of the signal with frequencies below 200 Hz. The filter gives all frequencies above this limit a voltage gain of 2. Use this information and the axis provided to sketch the frequency response of the filter. Okay, so we've got our graph that we need to complete. Now we're told that we're going to boost those parts of the signal with frequencies below 200 Hz, and all other frequencies above that basically have a constant voltage gain. Now this means we're looking at a bass boost active filter, and base boost active filters mean that we're looking for a particular graph shape. Now, we know that 200 is a key frequency, so if we look along the x-axis, we need to recognize where 200 is on this logarithmic scale, and that is here. So this is 200 hertz, and that's where things change. Above that, what we have is a constant value. So we can put in a line there, and it's good always to use a ruler as far as these questions are concerned. But below that 200, we've got a boosting area. Now, as far as these questions are concerned, you have to use a protractor, and you've got to make sure that your protractor is set at 45 degrees for this particular question. And then what you should do is draw your line. Now, just be aware that if you don't use a protractor, you're liable to lose marks on this type of question. This has got to be 45 degrees, and they will measure it with a protractor. Okay, you've got a tolerance of probably about 1 degree, but just be aware of that. You've got to use a protractor for this particular type of question. Okay, so for part 2, design a suitable circuit for this filter to create the best possible fit to the specification using the following components and no others: an op-amp, a 39 kilo ohm resistor, an 82 kilo ohm resistor, and a 10 nanofarad capacitor. Complete the circuit diagram for your design, and you're given just this part of a diagram. Now, what we need to realize as far as this is concerned, that this has to be an inverting amplifier. So we can actually draw the diagram to begin with. For an inverting amplifier. Where we've got our connections, and we know that we've got Rin and we've got RF. And because this is a base boost, then we need to know where to place our capacitor, and our capacitor will go on the top here. Now we know the capacitor is 10 nanofarads, but what we need to do is ascertain which of the two resistors is the 82K and which is the 39K. Well, because we've got a gain of 2, hopefully you can remember that gain is equal to minus RF over Rin. So the ratio between RF and Rin has to be equal to 2. And therefore, what we realize is that the RF is going to be our 82K, and Rin is going to be our 39K. And what we just need to do is state that underneath, that RF is 82K, Rin is going to be 39K, and C is going to be 10 nanofarads. And if we wanted to, we could check that. We could probably do an equation using the break frequency. And if you remember, the break frequency is F is equal to 1 over 2 pi RC. And in this particular example, the resistance value would be 82,000, and the capacitor value would be 10 times 10 to the minus 9. And if we did that, we'd get a value hopefully close to our break frequency of 200 hertz. I think if you actually use that equation, it comes out to 194 hertz, which is reasonably close. Right, okay, so for part C. Right, part C, big question, 6 marker. And reality, this is one of the easiest 6 markers that you'll see, because most of the information that you need to ascertain is pretty straightforward, but it's broken down. You've got to think in terms of 6 markers. You need a bit of a plan. You need to do calculations using the information given. You need to comment on the positives and negatives normally, and then it's about amendments. And I suppose you could break it down into a 2-2-2, but there's probably more things that you need to give in terms of information than the number of marks. Don't think I've just got to give six comments or 6 bits of information. That probably wouldn't cover everything that you need to do. All right, so the question is, here is the specification for an audio system mixer. Number of channels 2, input impedance both channels greater than 10 kilo ohms, voltage gain both channels variable from 2 times to 20 times. The following circuit is proposed as a suitable solution. I've got it here on the screen. And it says evaluate this circuit as a solution that meets the specification given above. Okay, so we can deal with the first part of that specification, number of channels. Okay, so number of channels. And it's got 2 channels. It's got CH1, CH2, and this means that the specification is met. And that might seem really, really straightforward, but they've asked you to see whether the solution meets the specification, and you need to state that the number of channels has been met. Okay, what about input impedance both channels is greater than 10 kilo ohms? Well, because we're looking at an inverting negative feedback amplifier, then the input impedance is given by Rin. Now we've got for both those channels an Rin which is a variable resistor, and we've got to assume that goes from 0 to 100k, and a fixed 15k resistor. So the minimum resistance of Rin is 15k. So the input impedance is 15k as a minimum to 115k as a maximum. And what this means, again, is that the specification is met. But it's the last part of the specification that would hopefully give us a little bit more information to play with. Now, what this means is that if we think of gain for this is minus RF over Rin, and at minimum, what we're going to get is minus 300 over 115. And at maximum, we're going to get minus 300 over 15. Okay, so what values does this give? Well, 300 over 115, I believe, is 2.6. So the gain at minimum is going to be 2.6, and the gain at maximum, well, that should be 300 over 15, is going to be 20. Well, the specification was asking for a variable of 2 times to 20 times. And what does this mean? It means that the specification is not met. So what we now need to do is give amendments. And to meet the specification, what amendments are we going to give? Well, what we can start with is at a maximum, we need a gain of 20. And to get a gain of 20, we need a ratio between RF and the fixed resistor. So if the variable resistor was 0 ohms, we need a ratio of 20. So as the minimum size resistor that you should be using is 10k, if we basically just call the Rin value of 10k, then we'd need 200k in order to give that maximum voltage gain of 20 times. Now you've got to think in terms of the other extreme in terms of the range, a voltage gain of 2 times. What value would the variable resistor need to be in order that the total Rin was half of RF. And hopefully you can see that the variable resistor would need to be 90k. And then we just need to ensure that we label the rest of the resistors. And what we've there got is the amendment to meet the specification for the last part of the specification, and that should conclude question 3.